Hey everyone, welcome to episode 5 of Everyday Physics. Today we're going to be looking at forces. There's 5 basic forces. The first one's the force of gravity that Earth exerts on every object that always points directly down. The second one's the normal force, which is the force between two surfaces. For example, the ground is putting an upward normal force on me right now. The third one's the force of tension, which is the force applied by a rope, string, or spring. The fourth one is the force of friction, which is the force between two surfaces that are moving across each other. And the fifth one is the applied force, which is a broad category that we use to describe any force that a human puts on an object. Newton's first law tells us that if the forces are balanced on an object, it's either going to stay at rest or move at constant velocity. Here I have a box rigged up with some rope and a weight. And I'm going to drag this box at constant speed, and then we'll take a look at the forces on that box. When I was dragging the box, it had a downward force of gravity from the Earth, an upward normal force from the ground, the force of tension that I was pulling, and then a force of friction the other way. Let's go look at a force diagram. Here's the force diagram for the box. We got the force of gravity pointing down, and that's from the Earth on the box. The normal force pointing up from the ground. The frictional force, opposite the direction of motion, also from the ground, from the box scraping across the ground. And then the force of tension from the rope on the box. Now this force of tension is at an angle. We can name that angle theta for our calculations. We know, according to Newton's first law, that if an object's moving at constant velocity, or at rest, all the forces on that object must be balanced. So what I'm going to do is I'm going to redraw this force diagram, except I'm going to separate the force of tension into two components, a vertical and a horizontal component. So here we have that. Gravity, friction, normal didn't change, but the vertical component of the tension is going to become the force of tension times the sine of theta, and the horizontal component is going to become the cosine of theta. Now, since we know the forces have to balance, since it was moving at a constant velocity, we can set up some equations. So to balance the vertical force, we know that the force of gravity has to equal the sum of the normal force and the force of tension times the sine of theta. So basically all downward force has to equal all the upward force. Horizontally, we know that the force of friction has to equal the force of tension times the cosine of theta. Just left has to equal right. To keep things short, sweet, and simple, I'm not going to actually do these calculations with these equations, but if you took a few measurements, like theta and the mass of the box, you would be able to plug in those numbers and solve these equations for the force of tension, the force of friction, any force you wanted. Okay, here I have a small kitchen scale and a glass of water. So how scales actually work is rather than detecting what the weight of the object is, they instead detect how much normal force they have to put on the object. So I'm going to put this glass of water on the scale. It looks like it's around 520 grams. Now, if I just apply a slight force upwards, we see that the number drops. If I apply a slight force downwards, the number increases. Let's look at a force diagram to find out why. Here's a force diagram for the cup when there's no forces on it from me. We have the gravitational force downward from the Earth and the normal force upward from the scale. Now remember, what the scale is measuring is the magnitude of this normal force that it has to put on the cup. When I applied a slight force upward, the force of gravity doesn't change. What changes is the applied force that I put upward makes the normal force that the scale has to put on it smaller, because remember, the sum of these two upwards forces has to equal the downward gravitational force. So this made the reading from the normal force smaller. When I pushed down, again, the gravitational force never changes. What happened was there was an applied force downward, and now the normal force that the scale has to put on the cup upward increases due to this increased downward force, causing the reading to be bigger. Thank you for watching. Hopefully you enjoyed this video and learned something. Have a good day.